Okay, good morning. So I have brought back the first assignment marked by Tom ChE. He's one of the TAs for this course. And the other one is Yuha. And the second one will be marked by Yuha. So what I would like is, I had a discussion with him, and I think he's quite happy with the way that the first assignment turned out. But if you have any questions or concerns, you should first address it to him, and he can explain to you the grading scheme. And then if you're still unhappy with it, then you can come and talk to me about it. But hopefully it will be resolved by discussing it with him. And I don't think there should be any major issues, because he seemed to be quite happy with the way that everybody did. And he said it was, most people got somewhere between 17, 18 or so out of 20 points. One of the things I wanted to discuss first is, the quiz, I have not completed it yet. I'm working on a 1 week turnaround. Okay, so last week's assignment will be handed back to you this week, and then I have put up the third assignment today on Moodle, last night. So that will be due next Thursday. And the third assignment is not about chemical processes as much, but it is about MATLAB programming. So building your MATLAB skills a bit more. And then the fourth assignment, we will switch back and I will build something on ordinary differential equations that we are doing currently. Okay. A number of people have requested additional tutorials on MATLAB. And so I'm now trying to find out what is the best time for majority of the people. I think in such a big class, it may be difficult to find a time that everybody is available, and I'm not even sure how many of you would need that. So let me just go through that quickly to find out what time would work best for you. So the red slots are already taken out because I'm committed at those times. All the white slots, Monday, Tuesday, Wednesday, Thursday, Friday, and I've thrown in Saturday as well. I'm willing to come for an hour or so on Saturday, if you guys are willing to do that.
How long are the sessions?
I'm planning on 1 hour. If you stretch it too long, your attention span will go down. So I do plan, but I don't promise, I do plan to record that session as well and put it on Moodle for those who are not able to attend. But if the attendance on those extra tutorials dwindles to 1 or 2, then I'll take that as a signal that you don't need any more help. Okay, at that point, we will discontinue. But if there is enough people attending it, enough for me is at least 4 or 5, then I will continue with that. So let me just go through it quickly. And I want a show of hand saying that you are busy. Okay, if a lot of hands go up saying that you are busy at that particular time, I will mark it as unavailable. Okay, so 8 a.m. Monday. Okay, let me 9. Okay, this may not work, but try. 10, 11, 12, 1, 2, 3, 4. I think 4 is probably, I know you would rather be somewhere else at 4 o'clock. 4:30? Okay. All right. Let's then mark it as well. Shall we try Tuesday at 8? Class? Well, we could do from 8 to 9 and then continue with the class. Okay, that's too much of MATLAB. All right. So you don't want 11 also for the same reason, right? How about noon? Put up your hand if you cannot make it. Okay, that's what I'm asking. 1. I know where it's leading. 2.
What
2, 3, 4, 4. All right. Wednesday 8. Nine. Some of you are holding it like that. Okay, noon. 3, 4. 4, I have fewer hands normally. Okay. Thursday, 8. You don't want that. You don't want that. 11, 2, 12. 1, 2, 3, 4. Again, only a few hands. I think I need to go for 7. I'm here. All right, 8, Friday. 9, 10, 1, 2. There must be an internet program that you can use to schedule that, right? 3, 4. Okay. How many of you want it? Tell me a solution. Saturday is a solution, right? On me?
I have nothing better to do.
On me? One at a time.
You have time, like, how many hours will you be available? And then we can figure out, like, exactly the work for everybody.
Well, we figured that out. Right? We went time slot hour by hour, and somebody is busy at some time, which I expected, I anticipated it. So, the options are to have a late evening class, maybe 6 to 7, or on a Saturday. What would be the preference? How many of you would like it on a Saturday? You want it, but you don't want to come. So I'm running out of ideas. Okay, I'm willing to do this, but maybe I have to let one of you discuss among yourselves and come back and give me a suggestion for a suggested time, and I will find a room. 6 to 7 would work.
Are you going to be here?
I'll be here. If you're willing to learn, I'm willing to teach, even at 12 midnight. Okay. So 6 o'clock, pick a day. Tuesday 6? No? You have a class.
Thursday at 6.
Thursday at 6? What?
Wednesday at 6.
Let's focus. How many of you cannot make it on Thursday at 6? You have a class?
Yes.
How about Wednesday at 6? How many of you cannot make it? Monday at 6. How many of you cannot make it? Okay, so I think by 6 o'clock, the number of people who cannot make it becomes, I think, fewer and fewer. Okay, so I'm going to go ahead with Wednesday at 6 because Tuesday and Thursday we meet anyway. So Wednesday at 6 o'clock. And those few who cannot meet, I apologize, but I will try to record it and post it for you so that you can listen to it. Okay? And we will start this from next Wednesday. I need to find a room, and then I will let you know. Okay? So let's agree that Wednesday at 6 for 1 hour. If you have a laptop with MATLAB installed, then you may want to bring it. Or I will try to see whether the lab in ChE building is available, the undergrad lab. So there are only 25, 30 stations there, but 2 of you can pull together and sit in front of it, so that as we are doing, you may also play with it, and it'll be kind of an immersive experience in MATLAB. Okay, so I will let you know. So, a TA hour? There are 2 TAs for this course, but I'm not asking them to take office hours yet, because I think they have a lot of work marking it, and so I'm going to try. If the load into my office becomes too much, then I might ask them to help a little bit. But I told them for now to hold on. And also by interacting with you individually, I know better what the problems are. Whereas if you guys go to him, I have no idea. So I want to be in the loop, learning loop. Okay, so I'm not asking the TA to set aside any TA hours. Okay, so we don't know how many we will have. We will see as time progresses. And one of the things that would be best is, of course, if you guys have access to MATLAB and you come up with questions and things that you want to learn, that you are having difficulty understanding. Okay, and that way it can be truly interactive. And I think the benefit of that will be in that. Otherwise, you could listen to the recorded lecture and do it on your own. But the idea of a lecture is that you should make good use of that time, not just passively sit and listen, but actively engage. Now, in the last, are there any questions so far on assignment 2? How many of you are, I think so far the traffic I've seen, people are doing all right, struggling a bit with programming, but doing all right. Any questions on the assignment? Number 3 is up. And it's about a bit more about programming, and it exposes you to not only we have seen for loop in the previous case. Now in this there are problems that will require you to effectively use a while loop and an if conditional execution statements. Okay? So there are problems that are designed to be used with that. I will demonstrate in this problem itself how a while loop works. Now, so the last class we looked at building the model, the process of building the model for a molten metal that is being cooled in a crucible. And these are the 2 ordinary differential equations that we derived from an energy balance, a transient energy balance. It is a dynamic model, but a lumped model, there is no spatial variation. That's an assumption. And we saw how to put that or cast that in the form of a matrix, vector matrix multiplication, for a differential equation. Previously, we have seen for algebraic equations. Now we have done that for a differential equation. And this system is a system of linear equations. And so A and B are matrices that are constants. Okay. So the question now is, how are we going to solve this in MATLAB? Okay. So I'm going to basically focus on how I would build the MATLAB procedures to solve such systems of ordinary differential equation. Okay, just like FSOLVE is a very powerful solver for solving nonlinear algebraic equations, any size, okay, but consistently formulated, meaning number of unknown variables and number of equations must match. The same thing here. There are a number of programs, not just like FSOLVE. There is something called ODE 4.5, ODE 1.5S. There are many programs. The theory behind it we are going to see later in the course. I'm still kind of preparing you to solve problems and then understand how these methods work a little bit more in detail. Okay? So, are there any questions on what we have done so far? How to formulate it as a vector matrix? And these are called initial value problems because at the initial time, t equal to 0, we need to know what the initial states are for the 2 variables that we have in this problem. So when I say I want to solve this, what I really mean is construct a solution where I can plot t1 as a function of time and t2 as a function of time. MATLAB has plotting routines that are built into the solvers so that it can generate the graphic automatically for you. So T1 starts in this case, for example, at 200, and I want to construct how does that profile look like. And T2 starts at somewhere 25, and we saw that through the TPS exercise that the profile might look like that. And our job now is to construct those profiles, construct those curves by using MATLAB solvers. Before that, let's explore what would happen to the steady state. What do we mean by steady state? What do you think? Things are constant, right? So in this case, the temperature must remain constant with time. Okay. So what would happen is if you wait long enough in real life, things will not change. You will reach a steady state. That means the profile then remains constant like that. Okay. When that profile remains constant, what happens to the derivative? Zero. So to obtain the steady state solution, all we need to do is the steady state solution has automatically been built into this model. If I set the left-hand side equal to 0, drop that completely because there is no rate of change of temperature with time. dt is equal to 0. And then what I will get is this is equal to 0 at steady state. Then how would I solve for steady state temperatures? What operator would you use in MATLAB or in linear algebra language? You would get the steady state solution as theta is equal to minus A inverse B. Right? Because A theta times B is equal to 0, first move B to the right hand side and then invert A. When B goes to the right hand side, you get minus B, and then invert A inverse B. So in MATLAB language, to get the steady state profile, all you need to do is in MATLAB, you will say A backslash B after you have constructed the matrices A and B. So the steady state solution is normally embedded into the dynamical solution. If you wait long enough, most of the times you will get a steady state. Sometimes you will not get a steady state at all, and we will see an example of that as well. Okay, so that is what we mean by the steady state solution. Theta is equal to minus A inverse B, which in MATLAB language will be minus A backslash B. But you need to assemble all the elements in A and B, but those are all known because these are all constants, H1, A1, M, CP1. These are all given. Okay, and this is given as well. They are numbers that you can calculate. Now, what do we mean by the dynamical solution? And that is what these curves are. Okay, so let's explore that a little bit. How would MATLAB, we want to understand, remember, when we did fsolve, we talked about how does fsolve actually solve it? How does it find that value of x which makes the f equal to 0? In the same way, how does ODE 45, this is a function that MATLAB is built in, which solves ordinary differential equations of this type. How does it do that? Okay. So start at the very beginning point. Okay. So starting at this point, I know, because at t equal to 0, I know the temperature is 200 degrees and 25 degrees. If I take, my question to you is the following. If I take those values and I know all these things, okay, H1, A1 and T infinity and H2, A2, but I don't know what T1 is, I don't know what T2 is. These are unknowns. If I take the initial value, 200 for T1 and 25 for T2, and plug it into the right hand side, and then I divide it by MCP1. M1 CP1. Here I divide it by M2 CP2. What would I get? You will get your rate of change of temperature with time at that particular time, t equal to 0. So the rate of change itself is going to change. That meaning the slope of this function will keep changing as time evolves. But at t equal to 0, when I put this 225, what I'm going to get is the slope at this point and the slope at that point. And you can do a very quick calculation. For example, h is 1, a1 is 1. Let's just make it simple. And t1 is 200 and T2 is 25. So what would be the rate of change? And M is 1, Cp is 1. Let's make everything 1. Okay? So what would be the right-hand side? Minus 175. Right? Because I'm making M1, Cp1, H1, A1. So this difference is 200 minus 25. And there's a minus sign. So what does that tell you? The temperature is going to decrease. It is a very large decrease. Minus 175. That is the gradient. And if I plug the same thing, similar expression into the second, that's going to tell me the rate of change of T2 with respect to time. Okay? And that will come out to be a positive number. Okay, it will be like this. And that's all I know. I know the initial value and I know the slope. So you need to tell MATLAB how to calculate the slope. That means you need to write a function, just like you wrote a function for fsolve, you need to write a function that calculates the right-hand side. Then MATLAB uses that as the slope, the local slope. If you know the slope and you have to calculate or predict the temperature at the next time point, how will you do that? By hand. Approximately. You would use a Taylor series. You know what Taylor series? It's very important in numerical methods. The Taylor series is not very, one-term Taylor series is not very difficult to understand. Okay? What does the Taylor series say? The Taylor series simply says that T1 at time 0 plus I am going to choose a small time step, delta t, is equal to T1 at time 0 plus dt1 dt multiplied by delta t. Plus there are other terms, higher order terms. Okay, if I can calculate the higher derivative, then I can use the second order terms. But this is just to simply understand what MATLAB does to get a solution. So what you have done so far is you know the initial condition, 200 degrees. And you have just calculated at t equal to 0 what the derivative is, minus 175. So you take a small step size, delta t. You choose that. Okay? You choose that delta t. Then you multiply that delta t with the number that we have for the rate of change, which is nothing but the function itself, right-hand side itself. And that gives you what is the temperature at that delta t, slightly away from 0. Do you understand? Any questions on that? Absolute silence is not a good sign. Yeah.
So you're going to get a T1, and that's going to give you a new T1 at whatever point it is. You just have to keep doing this over and over until it's establish your curve.
You got it. So you then put a loop. This is why loop is very important. Then you just keep repeating it. Okay, now I know what is if I use this formula, I know what is the value of temperature at this point. So I calculate this derivative at that point. I calculate the slope at that point. And then I take the next step. Okay, so this is an approximate way of constructing the solution. And that's what MATLAB does. Of course, it does it with a high degree of precision. Yeah.
Is sigma t one variable or is that two different variables?
Good question. This is just one number. And that one number represents the step size. It's called the step size that I'm going to take. A small delta t. Delta t stands for a small increment in time. Okay? So we're using a lot of these concepts. What is delta t? What is the error? We'll talk about that later on. But at this stage, all I want is a graphical understanding in your mind of how this process works. So how would you calculate T2? The same process, right? Because you know by plugging it into the second function, you can calculate dt2 with respect to time, the temperature of the second function. Okay? So you would use this is the multivariate version of the Taylor series. So T2, 0 plus delta t is going to be equal to T2 at 0 plus dt2 over dt at 0 multiplied by delta t. There are higher terms, that's where the error comes. Yeah?
For T1, since B is 0, you would have division by 0.
Where?
For T1, like B is 0, right? So
Did you say B is 0? Oh, no. Okay, that's a good question. But what is your function? What is dt1 dt? It is basically the multiplication of this times p1 plus this times p2 plus 0. There's no division by 0. What is the right hand side of the function? And I will show you in MATLAB how you write this. Okay? But keep in mind that I have divided everything by M1 CP1. So all I have on the left hand side is dt1 dt in the first element. This is a vector representation. So there are two terms there. The top term will be dt1 over dt. The second term will be dt2 over dt. On the right hand side, I need to do this spectrometric multiplication. So A times theta. A is this, theta is going to be T1, T2. So this times T1 plus this times T2 plus 0. That is going to be this number. Okay? So there is no division by 0. Okay? So that is what MATLAB does. It uses a more sophisticated algorithm, but conceptually, in principle, it uses a Taylor series to advance from one time step to the other step. And now that you know what the value is at delta t, as he said, put a loop around it and you repeat the process and you can construct the whole solution. What it means is that the ODE45 is the name of the function, like fsolve. It is going to need to interact with the function that you are writing. So always, MATLAB doesn't know what problem you're solving. So you need to describe that problem by writing your own function. Okay, that describes what the problem is. Then MATLAB has the generic procedure that can integrate any ordinary differential equation as long as it knows how to calculate the right-hand side, the F1, F2, etc. Any questions? Let's get into MATLAB. Okay, so I need to implement this function in MATLAB, and I have put the piece of code. Maybe you let me take you through the code and ask you to decipher the code, understand what the code does. Can you see at the back? So I am going to write a function that takes n, two parameters, and sends out one parameter. So I'm declaring a function, f is the parameter that goes out, and time and the two temperatures are the parameters that come in. So in any ordinary differential equation, the first one is time, that is the independent variable. The second argument is a vector of length, whatever it is. If you're solving 4 ordinary differential equation, it should be a vector of length 4. So in this case, what should t be? Vector of length 2. Okay? So that comes in. And what is that value? It's the current state. So t initially will be 0. The small t will be 0 because the current time is 0. And the capital T will be 225. The first one will be 200. The second one will be 25. And then you are writing this function that calculates the F1 and F2 and sends it back. So when it goes out, F1 will have two values, function 1 and function 2. Function 1 is nothing but, like F1 is dt1 dt. And F2 is dt2 times dt. So it calculates these derivatives at that time and sends it back. So I think up to here it should be clear, right? What are we doing? Initializing whatever the parameters that are given to you. Okay. So in this problem, I'm taking H1, heat transfer coefficient, as 1, H2 as 1, A1 as 1, A2 as 1.2. T infinity is the ambient temperature that appears in the equation. So I'm defining T, I, and F as 25. M1 is 2, M2 is 0.5, and CP1 is 1, CP2 is 2, etc. Okay, so initializing everything that appears in the right-hand side of those two equations. Can you decipher what I'm doing here? What will I get if I enter that? The A matrix. Okay, so it's basically copying whatever I have. This is the first element of the A matrix, A11. There is a space between that, and then I have A12. So there is a space there. That's how it knows the first element and the second element. Now by hitting an enter, it automatically creates the next row. Okay? And in the next row again, this is A21, that's the space there, and then there is A22. Okay? And when I close that, MATLAB can interpret that as the end of input to that matrix, and so A would be defined at that time. And then what do I do in the next line? B. B is 0, semicolon, means go to the next row, and then H2, A2, T infinity, M2 over CP2. Now here I'm using the precedence ordering. Okay, so with M1 divided by M1 divided by CP1, because both of them should appear in the denominator, but you can do it anyway in a number of ways. You can put a parenthesis and then say M1 times CP1 if you like, in parenthesis. Okay, and the last statement, what does it do? It calculates the right hand side in one step, because it says A times C plus B. Okay, A I have defined here, B I have defined here. Where does C come from? Where is T defined in any of these? It comes into the function from the very top line. Okay? So what will be the first time that comes in? What will be the value of T? It will be the initial condition. So the initial condition has to be specified. Okay? In our case, the initial condition we said is going to be 225. So that's where the T comes in. Okay? Now, do we need the time in calculating this function? Okay? We are sending into this function time, okay, but we are not using the time anywhere. So for this function, there is no time dependence on the right hand side. But there are some problems where time dependence will appear. Okay? But MATLAB requires you to send these two in that particular order. The first argument should be time. The second argument should be the unknown vector. Question?
So is all that thing parentheses up top doing, is that all it's doing is calling from another function or script?
Yeah. So it's good. We are going to call this function, but we are not going to call. We are going to call the solver. The solver is called ODE45. And the solver is going to call the heat. But I need to tell the solver, this is the function I want you to solve. So I will tell the solver heat. So it's going to be exactly the same syntax that we use for fsolve, but the name would be different. Okay? And the principle that uses inside it for solving is completely different. The algorithm is different. So any questions on the function? I hope it's getting easier to write these functions and you understand the idea of how MATLAB works with these things, right? Now, how do I write the driver that's going to solve that? Here is the driver. Okay? So the key is I need to know this. Okay? What is the algorithm that solves ordinary differential equations? In this case, it's called ODE45. And ODE45 takes as the first input, just like fsolve, takes as the first input the name of the function that you have constructed. So it is ampersand sign and then the name of the function, heat. In this case, I'm storing it in a function called heat.m. Okay? I want you to guess now, what would the next parameter be and the next parameter? There are three parameters that we are passing. You must pass at least three. The first one is the name of the function. And then you must pass two of them. You may pass more than that. We will talk about it later on. Is there any one of the second or third parameters you recognize? This one is the initial condition. And this one is the time. What you are telling in this one is called a T-span. What it says is, give me the solution starting from time equal to 0 in steps of 0.1 going all the way up to 100 seconds. Okay? Start at 0, give me the result every 0.1 second, go up to 100 seconds. Give me the result. Okay? What does ODE send out after it computes that? What is the meaning of the term on the left-hand side? What would be, can you guess, what would be contained in that? These are the outputs from ODE, the placeholders for the output from ODE. Anything that appears on the left-hand side is an output. So that program is going to dump or assign values to these two variables. The first variable is the time. the time at which it spits out the results. Remember, when you're going to generate that graph, on the x-axis what you're going to have is the time. Okay, so you need that. On the y-axis what you're going to plot is the temperature of both variables, T1 and T2. So T will actually be a matrix. Okay, the first column will contain T1 at various times. The second column will contain T2 at various times. Okay, and then you can plot. So the next command is basically plot, and you know how these things work. Any question? Yeah.
Once you call that, it will go back to that function. If you call it.
If you call this, if you execute this script, okay, at this stage it will transfer the control to ODE45. ODE45 is a huge program, and its job is to calculate the derivative at every instant of time and move to the next time step and repeat that. Okay, its job is to implement what we talked about in the Taylor series, and then it will spit out all the results. Okay, but ODE45 needs to know what problem you're solving, and that is defined by you in the function heat. So ODE45 and heat will communicate with each other, just like fsolve and the other problem communicated with each other.
You said that ODE45 calculates the derivative of the function?
Well, it uses the derivative. It doesn't calculate the derivative because it doesn't know what problem. What?
Does it plot the original function or does it plot the derivative?
It plots the original function. It gives you the solution. It doesn't know how to calculate the derivative, so it makes a call to heat. Call says, okay, at this time, the derivative is this. And then it says, okay, then now I'm going to project what is the next temperature at the next time step. It gives you a curve, right. It will give you the result which you can plot, or you can make it plot directly.
So you set in, I guess, your delta T with the 0:1.
Right, that's a very good question. Yeah.
So you don't have to, I guess, your temperatures, it knows that that's your initial values and then it goes from there. Okay. It's written in the ODE45, or is that written in the function file?
Well, ODE45 interprets the third parameter you pass as the initial condition to the vector. And it takes this as your initial time. Okay, so this can be generalized, and we will see how to do that. So ODE45 just needs to know what is the start time, what is the end time, and what is the initial condition at the start time. Optionally, you can specify, give the results at every point 1. Okay? I'm really simplifying it to get an understanding of how the process works, and then you will see and try to interpret and try to understand in greater detail what exactly it does. Any other questions? Yeah.
Yeah, once it calls it goes back to the first function that we wrote, and then it performs that, and then the ODE45 is going to.
Yeah, ODE45 is going to give you the solution, but by talking all the time to heat to get the derivative, local derivative. Okay, let's actually run it and set up a breakpoint and see how this works. Okay, I have a function called dr heat, which is the driver for the heat function. And you see a copy of it in the notes. And then I have a function called just heat. We went through each one of them. Okay. Let me just set up a breakpoint here in heat and run this program. Okay. And I want you to guess what would happen. That's the best way to learn about MATLAB. Project what you think should happen. If it happens, you understood it. If it doesn't happen, you think more. Why? What happened? And try to correct your understanding. Okay. So now I'm going to maybe set a breakpoint and start executing it. Now remember, this is just to understand. I'm showing you the debugging and the tracing. In an assignment, all you need to do is go to the workspace and enter the name of this function, dr_heat. Then it will give you the result. Okay. I'm just going to step through that. So I've executed it and it has stopped at line 2. Okay. So if I step, where does the control go? It goes to ODE45 because it tries to interpret it. It says, okay, I need 2 placeholders for time and a variable called t, and then equal to ODE45. ODE45 knows as a function, ODE45.m. So it transfers control to that function and also transfers the 3 arguments. So that ODE45 knows what these arguments are. So if I step, it went to ODE45, but ODE45 is, for our purposes, just like FSOL, it's a black box. Okay? So we don't know what it does in detail, step by step. It will be a huge program if you try to print it. Okay? But what has happened now? ODE45 has called heat. Okay? And then heat has executed all these things, and I set up a breakpoint here. So right now I've come to this place. This is something you need to understand. I have come to this place via ODE45. Okay, from workspace I call ODE45, or from the script file I call ODE45, and ODE45 has called heat, and it has come to this. Now what would be the value for T? 0. What will be the value for capital T? 225. Okay? And of course we are setting all these H1, H2, and we are defining A. Okay, and we are defining B. And if I step one more, I'm going to calculate F. So you can see that the first derivative is negative and the second derivative is positive but very high, which tells you that the crucible is going to heat at a very high rate, whereas the molten metal is going to cool at a reasonable rate, minus 87.5. What would happen next if I step through? The control goes back to ODE45. Very important. Okay? A lot of people had difficulty understanding how FSOL works with your function. It's the same idea here. But when it goes back, what does it take with it? 2 derivatives. So it goes back, the F that appears here, okay, goes back in this to ODE45. And ODE45 must use then its scheme to project the next time and the next temperature. And out. Okay? So this is, where am I now? I'm actually in a function called ODE arguments. I don't know whether you can see it for some reason. Okay? So because I stepped it, I got into actually the function ODE45. As I said, this is going to be a huge function. Okay? And I don't want to go through examine this. It's actually a good idea if you want to go through that and understand it, because you get some very good programming practices. So I just continued from that. I didn't want to examine it because it works. Okay? The only problem might be with this. So I continued, and this is something I guess you should also follow. There are several icons there. The first one is step, which means step, execute one line at a time, stop at the next one. Whereas the last one is continue, which means continue execution without stopping until you hit the next breakpoint in your path of execution.
Did you hit step whenever the first time?
Yes.
Did it run? Because it ran all those variables.
It ran through it because I've set up a breakpoint here. I didn't set up any breakpoint before. So when it, yeah, go ahead.
I was just wondering if you could continue step.
I did not, because I have not set up anything. The moment it comes into heat, it executes all this and stops there. If you want, I can set it up there and see what happens next time. This is going to go on between ODE45 and heat many, many times. Okay? So right now, what do you think T would be? 0.0011. How did it pick that value? Is a good question. We will understand that only when we understand the algorithms for integrating ODEs. So there is something called an error. So it wants to control the error, and the error depends on your delta T. So if it had taken 0.1 as the step size, the results will be, the error in the result will be significant because it's too large a step size. Okay? Remember, the slopes are very high. So what we are doing is essentially, if you go back to that sketch that we had, where is that? This sketch, okay? The slope is the actual derivative at that point. But if I say I'm taking a very large time, then I continue the slope. So I'm going to predict the next temperature is here, but the actual temperature is there. So the larger the time step I take, the more error I would have. So in order to control the error, ODE45 says I need to actually use a very small step size, and it uses a very sophisticated algorithm to determine that. And so what it does is it takes an extremely small step size. It will adjust the step size automatically. If the error is small, it will take a larger step size. If the error is large, it will shrink the step size. Okay? And what do you think T would be? That is the temperature at that time, 0.0015, whatever that was. That is the temperature at that time. So it automatically brings back that as the initial condition and puts the loop that you talked about. Okay? So let's continue. What has happened now? Let's come back for the third time. Now T will be different again, 0.0017, and the temperature will be different. But I set a breakpoint, so it stops there. Okay? Right now, what would be the value of H1? What will be the value of H2? Right now, it will be undefined. Why? Because these are, even though it came through a previous time, it's a local variable. The moment it gets out, it erases all of them. So when it comes back again, it will reinitialize it step by step. That's why you need to put it inside this. Now H1 will be defined, but H2 will not be. Okay? So,
Could you hover on H2?
pardon me?
Can you hover over H2 real quick? Like put the cursor on H2?
Oh, H2,
Yeah.
there's nothing there.
Okay, so just
Okay?
come up.
And if you want to make sure, you can look at the workspace. In the workspace, there is a variable window there. So in that window, you have only T, uppercase T, lowercase t, and H1. Uppercase T and lowercase t come from the input, and H1 we just define. Okay, as you step through, you'll find that it defines one by one on that window. See, H2 appears now. Okay, A1 appears, A2 appears, all of them appear one by one. These are all local variables. And the moment you get out of this, let me step. So these are all the local variables in this function, the ODE 4-5 function. Okay. Let me continue. I think you get the idea, right? Any questions?
Is it plotting each?
It is not plotting anything. It is in fact not sending anything out because it hasn't come out of ODE 4-5. It is just marching from 0 in steps of 0.1 to 100 or something. Okay? So it's going to go through this maybe 200, 300 times. So let me take this out and continue and see what happens. But let me set a breakpoint here. Okay? So continue. Now it has come out of ODE 4.5. Okay? So what does that mean? It has done the integration from 0 all the way to 100, time of 100 seconds. Okay? And it will have, you can see here, it will have lowercase t and uppercase t. So ODE 4.5 has generated the numbers and put it there. So how many elements are there in ODE, in these two variables? Lots of them, right? So if you double click on that, it shows t. This is how we want it. Starting at 0, 0.1, 0.2, 0.3. Okay? So give me the output at those time intervals, go till 100. Okay, so it did that. And the T is the temperature. The first column, as I said, will be the solution for T1. Starting at 200, it decreases. Starting at 25, it increases. Okay? These are the temperatures at those times T. So you can take this and send it to the plot command, and you'll get a plot out. Okay? So if I step one more time. There. Okay? So it's actually a very easy job for you to solve any ordered differential equation of any size. Okay? Now, does that figure make sense? This is what you did in the TPS exercise, trying to predict what would it look like. We said that T1 should decrease monotonically. T1 will increase and then decrease. Okay? And it in fact happens, but it happens so rapidly that you probably don't see it. Right? So T2 increase very sharply and then decreases. T1 decreases continuously. Okay? You can zoom in if you want using the zoom button. Yeah. Okay. Yeah.
I had a question about the local variables. Are they clearing because you're leaving that function, or are they clearing because you're calling a clear command?
No. It is by design. The moment you leave a function, it is deleted, expunged from the workspace. Yeah.
Just out of curiosity, if we're doing a program or homework and we create 1,001 variables in command window, we don't have to print that out, right?
You don't have to print that out. No. You would have to produce a graph. Yeah.
When you zoomed in on the green curve, it said on the x-axis it had negative values.
Right.
The x-axis is time, right?
Yeah.
So how can you
That it doesn't have any graph. It just reinitializes the axis. Okay. I am only zooming in from 0 to, in this case, about 6 or 7. Okay. So the automatic axis scaling takes it from -5 to +5 to the next number, but the graph itself will not appear to that number. It appears only at 0. Okay. So it's just a matter of axis, and you can reassign the axis. There are, as I told you earlier, if you go to edit and then properties, figure properties, or axis properties, I guess, you can change anything you want at this stage. You can rescale the axis and it'll replot it for you.
Is that TT started from 25?
Which one? Yeah, I closed the plot. Yeah, the T2 would start at 25, shoot up, and then come down. Now you understand, what do we understand so far? How to formulate the problem, how to write the mathematical equation, how to develop it for MATLAB, how to get a solution. Now you wear the hat of a process engineer and say, okay, what does the result make sense? What would happen if I change a few parameters? I'm going to ask you to think about that so that you can develop your intuition along those lines, okay? So let me close these. Any questions so far? Okay, I'm going to do this. H2 equal to 0. Okay. Now you need to think, as I said, a process engineer. So what does setting H2 equal to 0 mean? We need to look at the equation. So in this equation, if I set H2 as equal to 0, I'm saying that there is no heat transfer from the crucible to the surrounding. If you remember the figure from the last lecture, this is T1 and this is T2. And we said there is heat transfer from T1 to T2, which is governed by H1, and then T2 to the surrounding, which is governed by H2, the heat loss. So if I set H2 equal to 0, there is no heat loss. Okay. So what do you think would happen intuitively? If I take the crucible and then put an insulation around here and allow no heat to get out, what do you think will the final temperature is? I'm starting from the same initial temperature, 225. 200 for the molten metal, 25 for the crucible. Pardon me? It will reach a median temperature that depends on a lot of the properties. Okay, what is the heat capacity of the crucible? What is the heat capacity of the material, etc. So it will not go to 25. If I have this, if I have a mechanism to lose heat from this to the surrounding, the eventual steady state temperature will be 25. Maybe I should run this so that I show you what the steady state temperature looks like also. Let me do this now up to 500. Instead of 100, I say go up to 500. But instead of 0.1, I say go in steps of 1. So that I have 500 steps. Okay? And I save that. And I can get rid of these. And then execute that. So now I ask the question as a process engineer, how long did it take for this to reach room temperature? About 50, 60 seconds or so. And in this region, the temperature doesn't change with time. So that is your steady state. So if you want to get a solution to a steady state problem, this is another way of doing it. Instead of using fsol, You can formulate the corresponding dynamical problem, but integrate T to infinity, you get the steady state solution. But in this case, the steady state solution is almost 25 degrees because I have a heat transfer mechanism, okay, to this environment. Do you understand that? Any questions? So what would happen if I change that to 0? I guess I didn't save this. That's right. Okay. Okay. So I'm going to run this again. I think I'm doing something wrong here because I have a pause command. You know what a pause command does? It just pauses it. So I have several pause commands. I need to get it up. Okay. Let me put a comment on all these so that I don't need that now.
Why would you need a pause command?
Pardon me?
Why would you need a pause command?
Oh, I was going to see two graphs. I want to see, if I don't have the pause command, it will create the first graph and overwrite it with the second graph. I wanted to show you each one of them. Okay. But right now I'm focusing on the first graph. The first graph is called the time series, where you're plotting the state, in this case, which is T1 or T2, the two temperatures, against time. So such a graph is called a time series graph. Okay. So I have changed the heat transfer coefficient to 0. I'm going to rerun this, and as you pointed out, I want to see what is the final temperature look like. We know that it is not going to go to 25. Does that graph make sense? We started off at 225. 200 for one and 25 for the other. So there should be a time where the temperature changes and then reach a mean value somewhere in between, right? Is that what is happening? The answer is indeed it is what is happening, but I've integrated for too long, 500. So if I zoom in, I should see the graph that is coming sharply down from 200 to this value. The final value will be 184 in this case. Okay? And the other one coming from 25 to changing. You can actually see the discrete nature. Okay? This is how it projected the temperature gradient, and this is where it projected the next temperature to be. So it's actually stepwise. It's not a continuous curve. Yeah.
Is that an error, the fact that it actually gets hotter than the other one? Would that be an error? Or?
Error in what sense? That is, if I do the experiment where I put an insulator and I pour a molten metal which is 200 degrees and the initial crucible is at 25 degrees, from your energy balance equation, you should be able to predict what the steady state temperature should be. It should be based on the total energy exchange, right? So for steady state, what you will say is M1 CP1 T1 minus T infinity equals M2 CP2 T2 minus T infinity, some reference point. Okay. So you can calculate what you also know that the two temperatures must be the same. So you can calculate what this temperature is by simply looking at the steady state process. But from this model, the dynamic model also says what will be the final temperature and how long it takes to reach that. It gives you both pieces of information. So if I want to produce a smoother graph, what I need to do is, well, let me ask you, what will I do? This graph looks horrible, right? I don't get very many information. Why? Because I get a horizontal line and I get a very sharp rise with green and a very sharp rise in the blue. So I want to actually calculate those results accurately. What do I need to do? What do I need to fix?
Decrease the time and delta T.
Decrease, very good, very good. Decrease the time. Don't go until 500. Make the steps smaller. 0.01, for example. Okay? And by taking the step smaller, you're getting more accurate, smoother curve, controlling the error, and you will have a better resolution. So I'm going from 0 to 10 only now. Okay? In steps of 0.01, I see the curve is relatively smooth. And if you keep zooming in, you will see the choppy nature of the curve. That's always going to be there, okay? Because it is done discretely. We just need to do it, zoom it many times. Oh, still it's okay. All right, I give up. But it is basically doing by discretely. So it's basically, it's not a smooth curve, just line segments that are connected with each other. Okay, any questions? This is so-called time series, where you're plotting the state of the system against time. The state of the system, in this case, governed by two temperatures. There is another graph, and that is called the phase space or the state space. That is, what you can do is, instead of plotting temperature versus time, you can generate a plot which plots T1 versus T2 at every instant of time. So initially, you know, for example, T1 is 200 and T2 is 25. So that would be a single point in such a graph. Like T1 is 200, T2 is 25. And as they change, what kind of curve does it exhibit in this graph? So it may go like this, it may come like that. Oh, what am I? Pardon me? No. This will terminate at a point. Such a curve, when I plot that, will start at the point and terminate at a point. Can you imagine what those 2 points would be? It will be a curve. It will be a curve, but what will be the starting point and what will be the ending point on such a graph, T1 against T2? Exactly. I want to make sure that everybody understands that. Okay? The starting point of such a curve would be the initial condition, that is 225. But the steady state, whatever the final steady state, will be the terminating point. Okay? So let me plot that, and then I'll show you, give you time to think about it and absorb that. So let me get rid of those comments. And I can plot it without really calling, because I have already all the solutions. All I'm doing is here I'm plotting time against temperature, which is the time series. Here I'm plotting first column. This is where you need to get your MATLAB skills up, because what this means, what does that mean? The variable t already we saw has 2 columns. Okay? And so take all the rows. The column means take all the rows in the first column. That will be your x-axis. The second one will be your y-axis. All the rows in the second column. So plot T1 against T2. Okay? Let me just do that by typing into the workspace. Does that make sense? I said the starting point should be 225. So it started here. And then the temperature was going towards the end, the final steady state. So in this case, we set up H2 as equal to 0. Okay? That's why we get, as the temperature of the molten metal decreases, the temperature of the crucible increases in a nice linear fashion. Okay? But if I do the same simulation with H1 as not equal to 0 but equal to 1. Okay, so I run this again. So this is now with H2 equal to 1. So there is heat loss to the environment. And as you pointed out, the terminal point should be 25 and 25. Okay? And the starting point is 225. So this is, why did it not reach 25? I changed the time from 500 to 10. So it didn't have enough time to reach a steady state. I can plot that. Let me plot t comma t. So here I see. Okay. So the original function, the time series function. So I'm integrating only up to 10. There is still a gradient. Doesn't reach steady state. Okay. So if I integrate that to 100, then I will get the final term of the point as well. So you should know about time series, and you should know about what is called the phase plot, where you're plotting one state against the other state. Both of them give some useful information. What you should do at this stage is play with various parameters in that function heat and see how the response is. Change it, for example, change the mass to 1 or 2. Okay? So you will be able to see what is the maximum temperature rise in the crucible. That will change as you change M1 or M2 or CP1 or CP2. Okay? And also A1 and A2 are the areas. So if you change that, the response will change as well. So at this stage, we have devised a tool where a process engineer can come and do a series of what-if simulations to understand how the process responds dynamically as you change the various input parameters. Any questions? Okay. Let's move on to the next problem, which is also an ordinary differential equation. So, yeah, discuss the effects of property variation on the results. These are suggestions for you to play with. Okay? So, as you change the properties, CP1, CP2, how does the graph change? And what happens if the crucible is insulated? We also talked about that. Okay? The next problem is an example from MATLAB. It's called the van der Pol equation. This actually comes from electrical engineering. We're not going to go through the process of developing the equation, but we'll just take the equation and try to analyze it and see how we set it up for MATLAB. Okay? What is the first thing that you notice? How many equations are there? 2 equations in 2 unknowns. What are the unknowns? Y1 and Y2, right? And dy1 dt is the first function. And the function is very simple. It's simply y2. But the second function, which is the rate of change of dy2 with respect to dt, is a more complicated function. It depends on both y1 and y2. Okay? Would you call this a coupled system or an uncoupled system? What do we mean by a coupled system? If any variable affects all the equations, like y1 depends on what happens to y2, y2 depends on what happens to y1, then we call that as a coupled system. Okay? Each equation influences the other. So with that concept, would you classify this as a coupled or an uncoupled system? Coupled, because y1 is affected directly by y2, and y2 is affected by, y2 here is affected by both y1 and y2. Would you call this as a linear or a nonlinear system? This is a nonlinear system. Previous example was a linear system. This is a nonlinear system. Where are the nonlinearities? Is the first equation linear or nonlinear? First equation is linear. Okay, but the second equation has y1 square. That makes it nonlinear. And it also has the product of y1 square times y2. That makes it a nonlinear term as well. But if there is a nonlinearity anywhere in the equation, in any of the equations, the whole problem is nonlinear. Why? Because y2 affects y1. Okay, but y2 equation is a nonlinear equation. So the whole problem is nonlinear. And it's a second order, 2 first order equations, so I need 2 initial conditions. And those are given here. y1 at t equal to 0 is 2, and y2 at t equal to 0 is 0. How do I write this in MATLAB? You need to write the function. Okay, so I write a function called bpol, which takes as before time and a vector y, which contains 2 numbers, y1 and y2. Okay, and its function is to return f1 and f2 as defined by this. So you can see f1 is simply y2. Where is y2 defined? From here, from the input. Y will contain 2 numbers. It's a vector of dimension 2. And then f2 is 1000 times 1 minus y1 squared multiplied by y2 minus y1. So exactly the same equation. If you get this, you can then solve any ordinary differential equation. All you need to do is define the problem in the function. Okay. The reason I picked this is a nonlinear equation. Okay. Even though the method is the same, the method of solving it is the same. If I use this with ODE 4.5, which we saw as one of the solvers, it will not work. And we need to understand why it will not work. Okay? But there is another function called ODE15S. If you use that, then it will work like a charm. Okay? But the process is the same. ODE15S at V4. So this is saved in the function called V4.n. And then these are the time spans. I want to start from 0 to 3000. And these are the two initial conditions, 0, 2 and 0. So exactly the same way. Question? Yeah.
Should there be a semicolon between 0 and 1000? Or does it work like that?
It would work like this. In the previous case, I said I put a colon. So I said 0 colon, a time step colon, the end. Okay. I'll talk a little bit more about various ways you can specify the second parameter. This is called the T span, the time span. What time span you want to integrate. The minimum information you have to give is just this, the starting and the ending. But you can give more information if you want. Yeah.
Like if you pass the argument y comma t and then if you pass 2 0, does that work the same? Like if you pass yt and then 2 0 and 0 3000, is that function like for?
I'm not following. You mean in here?
Yeah. If you pass it the other way around, if you change 2 0 first and then 0 3000 and then
No.
yt.
No. The ODE functions require the first place to be the name of the function, the second place to be the T span, that is the time span, and the third one is the initial condition. The fourth one is options. I'll talk about options as well. So it has to be in that order. It will interpret only by the position. If you put 2 0 in the second position, it will take 2 0 as your time span. So it will start integrating at 2 and integrate backwards to 0.
Yeah, but if you change the y and t.
No, you cannot. Again, this expects the first position to be time, second position to be y. Yeah. Okay, so let's run this. Any questions on this? It's exactly the same. The only thing is the problem is different and it has a complicated behavior. Yeah.
So when you put VPOL, is it just saying you have some function y and t comma t? Is it all the same? You have t comma y, so you're saying you have
Right there. Yeah, this is saying that I have a function, being a rule of calculating the function f2 that depends on both t and y.
Okay, is it saying y is dependent on t? Is it saying like f is dependent on t?
F could depend on t. F will always depend on y. In certain problems, F could depend on t. Okay? But in this problem, it is not dependent on t. In the previous problem, also it was not dependent on t. But there are problems where in the ordinary differential equation, you would have y1 times sine t, for example. Okay? So this you will see in control course, where you are inputting a control action that is changing with time. Then you will have a problem where the right-hand side of f1 and f2 explicitly depend on time. That's why you need the time. So the program has been written. All these ODE programs have been written such that they can handle a wide range of class of problems. So in this case, we don't use t, but you must pass it to MATLAB. It expects the first position to be t. Okay. Okay, so here I have a driver for vpole. Okay, and let me set a breakpoint, and then vpole itself. And let me set a breakpoint there, and then I'm going to run the driver. So the driver called ODE15S, ODE15S called vpole. So I've come into vpole the very first time. So t would be 0 and y will be 2 and 0. Okay, and it will go back with f, the two function values, and then this iteration continues between the two. Okay, now I'm coming back with the second time. So t would be a different value. Still t is 0 in this case. So ODE15 sends 2 times the same value. I don't know why. Okay. So now t is, look at this. What is t? 0.00001465. Extremely small time step it took. Why? Because once you plot this, you will see there are very sharp changes in the y1 and y2. Okay? Let me just take this out and then continue. So I've come out of ODE15S and I have a vector of time which is 592. There are 592 time steps. And y, which is also 592. So I can plot one against the other by stepping through this. That is the solution for y1. The first column, y1 against time. Okay? So what do you see? Is there a steady state for this problem? There is no steady state. It's called an oscillator. Okay? It just has a sustained oscillation. And the oscillations are so that there is a period where it is changing slowly, and then there is a period where it is changing very sharply. When it changes very sharply, what happens to the derivative? dy1 dt. Almost, it's still defined, but it's a huge number, almost approaching infinity. Okay? So, that is why, because the derivative is high, it has to multiply it by an extremely small delta t. Because if I use this delta t and then project, if we take a large delta t, I will project the solution to be here. It will be totally wrong. So it knows that and automatically controls the step size. So ODE15S is called stiff ordinary differential equation. The stiff equations are ones that have extremely sharp gradients. Okay? And you can plot y1 against y2. Let me ask you to think. This is something for you to think. You know that y1 goes through these oscillations. And if you integrate it till 100,000, it will repeat this oscillation forever. Okay? Now, when I plot the state space y1 against y2, how should that look? This is y1 against time series. Okay? Now I am asking this question, if I plot y1 against y2, how should it look for such a periodic system that goes up and down, up and down? Not easy to guess, right? Let's see what happens. That's the beauty with MATLAB. There is no well, there could be a sharp gradient. The problem doesn't have any discontinuity strictly. It could be sharp gradient, but think about it this way. If at certain time I'm in this position, once I go through the same cycle, I come back to the same position. So I follow the same path in y1. That's going to happen in y2 also. So when I plot y1 versus y2, in that space, I start some position, I go wherever it takes me, I come back to the same. It's going to be a closed loop, not necessarily a beautiful circle. When will you get a beautiful circle? If it is a purely sine wave. Okay, if it's a purely sine wave, you'll get a circle. But now you'll get some strange closed loop. And that is called a limit cycle. There. Okay. You have sharp gradients, right? That's why the change is happening. And from this graph, you cannot tell what is the time. At what time will it reach this point, you cannot tell. Only from time series you can tell. But from this graph, you can tell that it is periodic in nature. It keeps repeating it.
So do you use step functions?
Good question, very good question. The step function is a discontinuity, right? So the theory for integrating ordinary differential equations has something to say about it. So you will have difficulty in integrating step functions. Yeah.
For the first assignment, when I was working on it, I printed out one and I realized I need to make changes to it. So I printed out the second one and I gave you the wrong one.